All right, let's continue talking about practice exam 3-1 with problem number 2. So if we look at this problem, it has two parts. And if we read through the information, we have a mechanism problem and then simply predict the reagents or identify the reagents problem. So here we need to come up with a mechanism. Here we just need reagents. Okay, so approach this problem however you want in terms of which part to do first, because they're independent of one another. So one way to approach it would be to say, all right, I think I can do the reagents part pretty quickly. So let's take a look at that one, and then we'll do the mechanism part second. So if we look at this one, we focus on what's changing. The left half of the molecule stays the same, so we can ignore that. The right half of the molecule, we have an alkene converting to an alcohol. Right? So if we look closely, tri-substituted alkene going to a secondary alcohol. So we have several ways to convert alkenes to alcohols. Right? So let's keep those in mind. Right? So if we're going alkene to alcohol, how can we do that? One, we can do sulfuric acid and water, so that's alkene hydration. Two, we can do our oxymercuration, demercuration. Or three, we can do hydroboration, oxidation. Right? All of those are going to add water to an alkene. Right? So when we think about it, which one of these is going to work? Where are we putting the OH? The OH is going to the less substituted side. Right? So if we think about these reactions and remember the regiochemistry, in these two, OH goes to the more substituted side. Another reason we know that it's not going to be the first one is that the first one goes with both syn and anti. Right? So this is syn plus anti stereochem because it goes through a carbocation. And when we look at this, we only have syn addition. All right? So it's useful when we look at the product to note we have syn addition, OH to the less substituted side. Okay? And hopefully by now we recognize hydroboration oxidation fits perfectly because that is a way to get syn addition and OH to the less substituted side. All right, so that's the answer to the second part. So that part is done, hydroboration oxidation. Now, if we go back and look at the mechanism part, this is a little bit weird. We haven't done reactions with I2 before, so that's a little bit different. Also, we're making some strange rings, so that looks a little bit weird. As we always do, let's number out atoms and see if we can make some sense of what's going on here. All right, so let's just number here. We'll start here. 1, 3, 4, 6, 7, 8. The right part of the ring, nothing happens, so we can leave that part alone. And then if we number over here, 1, 2, 3, 4, 5, 6, 7, 8. So if we look at what's happening, all right, we're adding a halogen and oxygen to an alkene. Right? And then hopefully you ask the question, have we seen a reaction in which we add a halogen and an oxygen to an alkene in one reaction before? And hopefully you recognize that we have done this before, where we've done our reactions of X2 and water. Right? And if we remember that reaction, right, we add halogen to one side, we add water to the other, and we do it in an anti-fashion. So if we look at what's happening here, right, this is clearly an anti-addition. All right. So perhaps thinking about this mechanism will be useful. And again, if we remember this mechanism, we remember that we form that cyclic halonium ion intermediate, right? And then we have water come in and attack. All right, so hopefully we have this sort of stuff floating around in our head. And even though we haven't done a reaction with I2, the fact that we've done it with Cl2 and Br2, we look at I2 and say, you know, that has to be the same type of mechanism. All right, so let's see what happens if we start rolling through this problem. All right, so if we have I2, again, the way we do this mechanism, the alkene is going to attack, the iodine is going to attack the alkene, and then I minus is going to fall off. Remember, we don't get rearrangement in these problems, so we're never going to form a true carbocation. Right, so now we can redraw. And we note the iodine's going back in the product, so let's just have the iodine going back. Right, so we'll have I going back. And we've generated I minus. All right, so there's our cyclic iodonium ion intermediate. Again, these are the intermediates we draw every time we do a reaction with X2, right? Whether it's just Cl2, Br2, I2, or it's those things plus water, right? And again, there's nothing else in here. We haven't added water. We could imagine the I minus attacking, but we've talked about how intramolecular nucleophiles often react faster than intermolecular nucleophiles. So we have an alcohol here, right? And it's reasonable to ask, well, are we going to add that alcohol to one side or the other of that three-membered ring? We know the answer because we can see up here we're going to react it with the 4 position. And again, when we do these mechanism problems, there's often questions about why is it doing one thing or the other. All we have to do is show how we can get to that one product. We don't need to worry about what other things might happen, because those could be happening. We just need to explain this one reaction. So now we can have the alcohol act as the nucleophile. That can attack carbon 4, open up the ring, right, and let's draw what we get. It's almost our target. And again, it's an anti-attack. We know that has to be the case because the I minus is blocking the bottom face. And if you think about it, we have a bond coming out at us where the oxygen is, so it makes sense that it's going to form a new bond coming out from the front as well. Right, the I is going back. And the only other thing we need to note is that we still have a proton on that oxygen. Right? Again, be very meticulous. Don't just have the proton fall off. Now in the last step, we can take I minus that we generated in the first step and have that come and remove the proton. Right? And then we get to our target. Right? So at first, this mechanism might look challenging. It's a complicated tricyclic structure. Right? We might get a little intimidated, but if you break it down, I hope that you can see very clearly that this is simply a modification of the X2 and water reaction that we've done before.